So in this video, we're going to recall the definition of the definite integral that we gave, give a little bit more of a general definition, and then go through some of the basic properties we use quite often of the definite integral. I'll also give arguments for why these properties are true. I don't view the arguments as something that are super important for a first semester calculus video or first semester calculus class to really focus on. That's why I provide them in the flipped class video. You should definitely understand what the properties are, but the arguments for why they're true, good idea to hear them once, but I wouldn't worry about memorizing them or anything like that. If you take further math classes, you might be more interested in them then. So for this video, we're going to consider y to be a function f of x on some interval a, b. We're going to usually consider delta x to be b minus a over n, so we're breaking it up into n pieces. And just like we've saw before, we'll take x0 to be a, and then we'll move across the interval in increments of delta x. So x1 is a plus delta x, x2 is plus, x2 is a plus 2 delta x, and so on, up until we get to the right endpoint xn, which is a plus n times delta x, which you can work out as just equal to b. So we saw before we defined the left and right hand Riemann sums is L sub n is we take the left edge of each of those and evaluate the function at that, and then multiply by delta x. So that gives us the area of the rectangles where the left edges of the rectangle touch the graph. In the right-hand sum, we have the right edges of the rectangles touching our graph. And so we define the definite integral if we just take the limit as n goes to infinity of these. So we just let we take more and more rectangles, which gives us a better and better approximation. And if we take the limit, we get the exact area if we're talking about a function that's bigger than or equal to 0. We saw other applications as well of what that could give us, but we define the definite integral as this limit. We could take left or right hand sums for this, and either of them will give us the same answer. So we saw that before. Now we're going to generalize this a little bit, which will make some things a little bit easier. It looks more complicated, but it'll make some of our arguments a little bit easier to do. So instead of just taking the left or right edge points, for each interval xi to xi plus 1, we're going to let xi with a star on the top of it just be any value in that interval. And we're going to choose a value in each of the subintervals. So from a to a plus delta x, from x1 to x2, and so on. We're going to choose an xi star for each of these. And then we can define the definite integral. Oh, this should be f of x dx there, not just x. That's a type. So this is a typo here. This should have a dx with it. This should be the limit as n goes to infinity of the sum from I equals 0 to n minus 1 of f of xi star delta x. So we see, instead of just looking at a left or right hand sum here, we're allowing these stars where we pick any value in there. So how is this generalizing what we've done so far? Well, if we were to take each xi star to be the left edge of the rectangles, then this would just give us the left-hand sum, because we'd see xi star is just xi, and this would be exactly the sum for the left-hand sum. If we take the star to be the right edge of each interval, then we see that this is exactly the same as the right-hand sum we've already looked at. And we can also recover the midpoint sum that we looked at briefly, and we'll look at more later, is if we take xi star to be the midpoint in each of these intervals, then this new, more general Riemann sum gives us the midpoint approximation here. So we can see writing this more generally with the xi stars allows us to get all of those different ones in one notation. So we don't have to write different notations for all of them anymore. And this is useful. Of course, if we want to actually calculate the approximations, we will have to pick what the xi stars would actually be precisely. But when we're doing more general arguments to show things are true in general, this just makes it a little easier to work with. So let's go through some of the basic properties now. So if I take the definite integral of a constant times the function, we can pull the constant outside of that definite integral. So geometrically, we think if we take an area and we scale it, it's the same thing as that number times the area. So let's see why this is true in terms of our formulas. So pick our xi stars as above. So the definite integral of c times f of x is this limit over this Riemann sum here. But now since c is a constant, I can pull it outside of the sum and I can pull it outside of the limit. So then I just get c times that limit. And this limit here is exactly our definition for our definite integral, so we can just replace it with the definite integral. So we see that's how we recover that property there. And the nice thing about doing it with the formulas rather than the area arguments give us good geometric intuition for why these things are true. But of course, we've seen before that the function isn't always necessarily going to be positive everywhere. So sometimes it might be below the axis and sometimes above. And then we have to worry about how that works if we're talking in terms of area, where the formulas here just allow us to get it regardless of whether f is positive or negative. Another property is if we take two functions and we take the definite integral of the sum of these two functions, it's the same thing as the sum of the two definite integrals. So same type of idea, the definite integral is the limit of this Riemann sum where we're summing the functions here, but we know we can break this sum of fxi star plus gxi star up into two different sums, and then we know that the limit of two sums is the sum of the limits, so we break this here up into this two things, and then we notice that this is the definite integral of f, and this is the definite integral of g. So pretty straightforward, just using properties of sums and limits. Now this one's geometrically easier to see than it is to see with formulas, but we'll see both ways. So if I take my interval AB and I pick any number between A and B, the definite integral from A to B of f of x is the same as the integral from A to C of f of x plus the integral from C to B of f of x. So let's start with some geometric intuition for this, because this one's much easier to see that way. So think of here's our function, say y equals f of x in the dark blue here. And the light blue is the integral from 0 to 2 of f of x dx. So all this theorem is saying is if I were to go, say, to 1 here, I can get all of the blue area by first looking at the area from 0 to 1 and then adding the area from 1 to 2. So that's pretty much geometrically obvious that if I take an area, I can break it up into two pieces and I'll still get the full area. The reason this isn't quite enough is, of course, we could have the function might not be positive everywhere, so it gets a little complicated. But when you're trying to remember why this is true, this geometric intuition is the way to think about why this property is true. So now in terms of our actual definition, this gets a little more complicated, but we know that since c is in the interval from a to b, it's going to lie between some xj and xj plus 1. So when we break it up into all of those pieces, it has to lie in one of those intervals. So for whichever one of those intervals it lies in, we'll choose our xj star to be equal to that value c. And so then when we write our definite integral out, we have just the definition here again. But now instead of going all the way from 0 to n minus 1, we're going to go from 0 to j, because then we know the last term, the xj star, is actually c. And then we're going to start this one at j and go to n minus 1. And we know the xj star here is c, so this one starts at c. So that means this one is the integral from a to c, because that's the last edge point we have. And this one goes from c to b because it's the first edge point we have. So that's how we would show that with formulas. But of course, like I said, the picture is the way to remember this one. So one more basic property we want isn't so useful geometrically, but it is useful in formulas quite often, is that if I have the integral, if I take an a and a b where a is less than b, and I have the integral from a to b of f of x, that's the same as negative the integral from b to a of f of x dx. So the way to see this is if we look at this second integral here, the only difference that happens anywhere is the delta x, because remember delta x is the edge of the interval minus the other edge of the interval over n. So instead of, for this one here, instead of b minus a over n, it's a minus b over n. Otherwise, everything is the same. So if I look at the integral from a to b of f of x dx, here's my definition where I'm going to put, instead of writing delta x, I'm going to write b minus a over n, because for this interval from a to b, that is my delta x. And then notice if I factor a negative out, I switch the order here from b minus a. If I make a minus b, then I pull a negative out front here. And now this is the delta x for this integral. And so we get negative b minus a. So this one, like I said, isn't so easy to think of what this means geometrically, but with the formulas, this is how this works. And this one's a good one. You're going to probably just need to remember this formula, that if you switch the order of the a and the b, you have to introduce a negative sign with that. So important to make sure you're comfortable and remember all of these properties of integrals, because they'll be useful and needed for everything going forward with integrals.